It's ready to go.
5 minutes of pain.
Okay, so we said these were the number 2 chromosomes, and these were the number 1 chromosomes. We said it doesn't really matter. We'll say this one's from dad. We'll say this one's from mom. We'll say this one's from dad, and this one's from mom. And I want you to realize something, because with regard to the production of these sex cells, the way that you get a ton of variation, because I think I was talking to Tyler. Tyler got done yesterday, and I was saying something to him, and maybe some of you guys caught it. Most of you guys, I think, were working on stuff. I go, this is the whole deal with sex and why it's so important to have it, because we said in natural selection, you have tons of variation that will allow for populations to adjust. So with sexual reproduction, you can get tons of variation. There was one method that I think we talked about the crossing over a little bit. If not, we'll discuss a little bit more. But basically, when all those homologs pair up, they don't go to one side or the other. If they did, we end up having a situation where, like, your sister is identical to you. We mentioned yesterday, Tyler, I go, you can have some people who are like, oh my gosh, my brother looks like identical to me. Then do any of you guys have siblings that look a lot like you, like very similar? Do any of you guys have siblings that look nothing like you? Okay, and that's the whole thing. If you just had cloning of the cells, or you had a very systematic thing where all the homologs paired up in one side and all the homologs paired up the other side, all the eggs and sperms from your parents would all be basically the same, and the kids would all be the same, but you don't want that. You want lots of variation, you want lots of change. And so I think what we said is on this one, did mom have big T or little t? Look at your notes.
Little T.
Mom had little t?
No, Mom had big T.
That's what I thought. Mom had big T, so we said this. Big T, big T. So dad had little t, little t. Dad had the dominant trait, though, for dark eyes, right?
Yeah.
Okay, so big D, little d, little d. So a couple things here I want you to realize, and this is kind of plays into that. I gave you that investigating inherited traits activity yesterday, because the one thing that you did is you all made those kids, but you were doing all this flipping of the coins, flipping of the coins, flipping of the coins. And I think you guys were okay with the idea that there's a lot of randomness in, any kid could be a boy or a girl, that there's a lot of variation with kids, but the flipping of the coin played to a more important part, because there's a thing called the law of independent assortment, and that goes along with meiosis. That goes to meiosis when you have these homologs pairing up. Our mom is not always on this side, dad is not always on this side. And I only have 2 pairs of chromosomes. I'm negating all the other 21 chromosomes that are on here, and I'm negating, we only talked about 2 genes. I'm negating all the other 29,998 genes that we have. I'm only picking 2 genes, but just with these 2 genes and these 2 chromosomes, I could put mom over here, and then dad over here. I could switch dad over to here and put mom over here, so that moms are both on this side. I could put dad on this side, and then keep dad over here so that mom was back on this side. You could switch up all those combinations. The other thing that can happen too is when you switch these out, just turning these to this side and this side, what happens is I have T's on this side, but if I change it out from these two to these two, I could end up having a little t on this side, and the big T and big T on this side. Okay? I could switch these out again, and if I did that, you'd have the little d on this side, little d on this side, and then big D and big D on this side. Or I can only switch out one or the other. So the whole thing is, as you go through each and every single one of these double chromosomes, it's a flipping of the coin. I've done it before out in the hallway, and because we have to have a half day today, it won't really work. And what I did is I said, I want everybody to, here, Alex, can you come over here and stand up? Just come over here for a minute. Just stand right here. So we're going to pretend we're like double chromosomes. Here, let's try and get here a little bit. So we're going to go double chromosome. Here, move over a little bit more. So that way, over there. So we're in the camera. So we're double chromosomes, okay? So we're together. Here, go together. Put your arms up. We're together during metaphase 1, right? Then we split apart, right? And then what happens is, and we can't do this in reality, but each one of these arms is sister chromatid, so we're going to do a no, you got to make okay? Which will separate during the final phase of telophase 2, when we separate apart, okay? So the whole thing is, go ahead and put your arm down for a second, stand here. I've had students and I go, hey, I want you to find somebody who's your same height and pair up with them, okay? Representing kind of like the homologous chromosomes. And then I want you to all line up, right? And then what I try and do is, I've done them where I've stuck little things, and I go, I'm going to give you a piece of paper, piece of paper, piece of paper, piece of paper. I give them all a piece of paper. One whole set of the papers was the recessive gene. One whole set of the papers was the dominant gene, but they all had the homologous chromosomes, had the same ones. And then I just said, get with somebody who's your like partner, or I want you to all get in line. And when they got in line, I went down it, and if you go through it, basically dominants weren't always on one side, and recessives weren't always on the other side. There was an even mix as you went down that whole thing. And if I kept playing that game over and over and over again, it'd keep flipping that coin. You'd have those flips back and forth, back and forth, back and forth. Okay? And so as you're flipping that coin, I'm going to have you guys make another baby with this in a minute. But as you make another baby, you'll see just by the flip of that coin. I know somebody said their baby was hideous looking, right? If you make another baby, you'll see the traits can be completely different, even though you start off with the same exact parents and they have the same exact genotype. Because of this pairing of this homologous pairing going in different orders, you're going to end up having a different kid. Okay? I want to show you one other thing that's kind of interesting. Go back to your double chromosome. Okay, get close together because we're in metaphase 1. Here's one thing that happened. These different arms, because we're X, we're in the double chromosome phase. There's something crazy that happens, and this is totally separate from when you flip in the coins independent assortment. This is a thing that adds another layer of variation. As we're together, we're going to get really close together. I know this is awkward, but it's fine. Okay? And what happens is these arms from these sister chromatids, here, tangle them up. They tangle and they tangle. They're supposed to tangle. And as they tangle, the areas where particular genes are kind of mix and they swap off genes. Okay? So when we come back, we'll kind of pull apart, and what ends up happening is this arm, this gene, can be pulled off and switched out with his arm. So that my whole genetic makeup is all the same, except for I now have the genes that are his arm, and he now has the genes that are my arm. Okay? So there's one other thing that happens. We're tangled up. It's called crossing over. We're crossing over. As we're going through crossing over, what can happen is that I can pull off. And what happens is my hand, the genes that are on my hand, rip off and go onto his body, except that I rip off about half his body. Okay? So where half his torso is, my hand's sticking out. Where my wrist is, half his body is sticking out. Okay? And in that sense, what happens is I have gained overall genes, so they call it an insertion. He has lost overall genes, so they call it deletion. So you have this crossing over, crossing over. Crossing over happens all the time, right? It adds a whole different layer of variation. But then in addition to that, we have deletions and insertions that can happen with all that crossing over too. Okay, so it's kind of cool. So when you sit there and you go, well, why is it like this? Why do I look like this? I look not like my parents. I do look like my parents. I don't look like my sister. I do like this. I have deafness. I don't have deafness. You have mutations. You have crossing over. You have independent assortment. You have deletions. You have insertions. You have completely different types of inheritance modes as well. So it's kind of cool. There's a lot of different things that play in inheritance, but it's all about sexual reproduction. If we didn't have sexual reproduction, you'd basically be spitting out clones of yourself, and each one would be identical. And we already talked about in natural selection, you don't want to have the same thing over and over again because it doesn't allow you to adjust to variations in the environment. Okay? Give Alex a round of applause. Thank you. You can turn it on. Go ahead and get out the cut and paste one.